Now we're going to talk about family of orthogonal trajectories. How do you find the family of orthogonal trajectories where every curve is perpendicular to every curve in the original family? So I want to deal with these two examples. Here is a family of curves. So I want to find the family of orthogonal trajectories. So I want to take the derivative. First step, take the derivative. So this would be 2c1x plus 2y y prime equal to 1. So I want to get rid of this arbitrary constant. So in this case, c1 x squared equals 1 minus y squared. Divide both sides by x squared. So I can replace this c1 with this 1 minus y squared over x squared. So this would be 2 times 1 minus y squared over x squared times x plus 2y y prime equal to 1. The x's cancel out there. So let's solve for, by the way, the derivative of 1 should be 0. So this should have been a 0 there. I got going too fast on that one. So let's solve for y prime. Well, divide everything by 2's. The 0 divided by 2 is still 0. So I have y prime equal to, take this over to the other side, becomes y squared minus 1 over x. So divide by y here, so I get y prime equals y squared minus 1 over x times y. Now, that's the differential equation for the original family. So what's the differential equation for the family of orthogonal trajectories? Well, it's the negative reciprocal, right? So that would be x, and for now I'll write YOT over, I'm going to put the negative in there. The negative of y squared minus 1 is 1 minus y squared. So there is the differential equation for the family of orthogonal trajectories. So this one obviously is separable. So take this over here. So now I'm going to drop the OT if you don't mind. So this would be 1 minus y squared over y dy cross multiply by the dx x dx. So 1 minus y squared over y dy equal to x dx. Now let's integrate both sides. Well, notice this is dy over y, so that's natural log of y. Absolute, I'll put the absolute values in there. Y squared over y is y, so this would be minus what? Y squared over 2 equal to x squared over 2 plus c. Now, if you want to, you can multiply everything by 2 and take this guy over the other side. So what do I end up with? I end up with 2 times the natural log of the absolute value of y equal to x squared plus y squared, because I'm multiplying by 2. And this arbitrary constant, 2 times an arbitrary constant, is still an arbitrary constant. And to avoid it being the original one, I will call it C2. So I end up with 2 times the natural log of the absolute value of y equal to x squared plus y squared plus C2. There's my family of orthogonal trajectories. So every curve in here will be orthogonal to every curve in here. Let's try this one. So first step, let's take the derivative. So think about it. So this would be over tangent x plus c1 times the derivative of the inside, which of course is just secant squared x, because the derivative of a constant is 0. But I have the same trouble there. I've got an arbitrary constant in my differential equation. I don't want arbitrary constants in my differential equation. I never had them before. I don't want them now. So I'm going to come down here and I'm going to use the definition of the natural log. So this is e to the y equals tangent of x plus c1. So therefore c1 equals e to the y minus tangent of x. That just comes from the definition of the natural log. So I'm going to plug it in here. So this one will come down here. So y prime equals secant squared x tangent x plus, plug in c1, e to the y minus tangent x. So the tangent x cancel. So I have secant squared x over e to the y. Now, let's find the differential equation for the family of orthogonal trajectories. So again, it's the negative reciprocal, and I'll start off by writing the OT there. So I'm going to flip it and negate it. Now, secant squared is in the bottom, so this is really negative e to the y OT times what? Cosine squared of x. Because 1 over secant squared is cosine squared. So now that is again separable, and I'm going to bring it here. So I'm going to drop the OT again as I did before. So I'm going to get dy over e to the y, because that came over here. Since it's in the numerator here, it comes in the denominator on the other side. Cross multiply by the dx, so I have minus cosine squared x dx. Now, this one's easy to integrate. This one, you got to remember your formula from calculus 2. So that'd be minus quantity 1 plus cosine 2x over 2. So now let's integrate both sides. So what do I get here? I get negative e to the minus y. I've got integral of a sum is the sum of the integrals. So this would be minus x over 2. Cosine 2x, I need the 2, so divide by 2. So this would be what? Minus sine 2x over 4 plus c. So if you don't mind, here's what I'm going to do. I'm going to multiply everything by a minus 4. Multiply everything by a minus 4. So what do I get? I get 4 times e to the minus y equals 2x, because the 4 over 2, the minus. 4 over 4 is 1, minus a minus, plus sine 2x. And again, I have a new arbitrary constant. I'm going to call it C2. So I have 4 times e to the minus y equals 2x plus sine 2x plus c sub 2. Again, I call it c sub 2 because this one was c and that one was c sub 1. So that's how I find the family of orthogonal trajectories. So every curve in here is orthogonal to every curve in there. So the steps are very simple. Take the differential equation of the original family. Make sure that you replace the arbitrary constant. There is no arbitrary constant. Then take the negative reciprocal to have the differential equation for the family of orthogonal trajectories, and then solve that new differential equation for the family of orthogonal trajectories.